So thanks for coming, everyone. I'm Ian Sayers, the 3D scanner product manager at Hawk Ridge, and I'm joined here by Matt Fisher, an application engineer, and he specializes exclusively in 3D scanning applications.
Pleasure to meet
So
you.
last month, we did a webinar where we overviewed a bunch of scanner technology types, and we discussed, on some level, how these scanners work internally. And this is one of 4 deeper dives that spin off from that overview. So we talked about how scanners work, we talked about modeling from scan data, and inspection methods. So this is one of those 4 spin-offs. If you're interested in a more general overview of the internal functions of scanners, you can find that recording posted on our site. And we'll have 3 more installments throughout the summer months. The next will be a 2-part series in June and July that focuses on creating CAD models from scan data, both with organic and prismatic geometry. So, freeform stuff, like, maybe a sculpture or a human body. And on the other hand, prismatic geometry like you might find on your average machined part. And then we'll also have a deep dive in August on inspection and quality assurance. So be sure to join us for those if you're interested. Today, we'll be taking a deeper dive into a few important aspects of how these scanners work and how these differences can affect how good they are for certain tasks. So we'll have plenty of time for QA on any subjects you want to ask about. And please do feel free to use your control panel to ask as many questions as you want during the presentation as well. So I'll spend most of my time today talking about a function called tracking, because I consider this the single most important aspect that isn't typically detailed on your average brochure. So it's kind of at the top of the list of things I wish I had understood better when I first started looking at scanners years ago. There are plenty of other factors that matter just as much, like accuracy and resolution. But those are a little easier to find on your average sales brochure, and they're easier to map onto your requirements. So for instance, you make electrical connectors with pins that are a certain diameter. Well, you need to look for a scanner with a matching stated resolution of that size. You have a tooth out accuracy requirement. You look for a device with that stated accuracy over that size range. That's a little oversimplistic, but that's the general idea. Whereas tracking, it's a little harder to detail in a concise sales document. So it's usually kind of behind the curtain, and you usually don't find a lot of info on it on sales-facing documentation. But it's really important, and it kind of dictates what objects you can scan, how accurate your scans are going to turn out, and how much prep and effort is going to be involved. So what is tracking? Tracking is a way of relating the data that's collected to data that's previously collected. So most scanners don't know their position or orientation in space. So the first data that's collected is just in an arbitrary position and location. And all the subsequent data is mapped onto that first bit of data. So you can think of 3D scans like panoramas. They're 3D panoramas, and each picture has to be aligned with those taken before it in order to create a contiguous image. So that's done by recognizing and relating features in one picture to those same features on another picture that overlaps with the first. Same principle as a panorama, and scanners do this in multiple ways in real time. So this is one way of doing it, one of the oldest and probably the least attractive. You put stickers all over an object, and then the scanner uses algorithms that recognize the patterns in the stickers and uses them to align the data as it's collected. It's fairly easy to see the drawbacks of this method apart from the ongoing cost of these special stickers. This isn't an option with all objects, obviously. Stickers may not stick to certain things. They won't work on highly curved features. You may not be allowed to put stickers on certain objects and so on. So, but it is a fairly simple from a technological standpoint, and you'll see this a lot with various types of scanners, both laser and structured light scanners, usually handheld, but not always. Because 3D scanners can't typically scan clear objects, here they've masked up some of the clear features like the headlights and put stickers on top. In an alternate setup, they have used talc spray to make the clear objects like the lights opaque. And often you need talc spray to cut down the shine. For instance, on a black shiny car, that's a problem for almost all scanners, and you would probably need spray. So you would apply the targets, and then you go and painstakingly clean off all the targets. So it can be, applying the stickers is time consuming itself, but when you couple it with a shiny object in the spray, it gets a lot more labor intensive. And that's one of the reasons why I consider it one of the less attractive methods. Another method of tracking and aligning data is to track a handheld device with an external tracking device like this laser tracker. These are incredibly accurate over long distances, and they have the advantage that the tracker can be used alone like a giant CMM. So you can touch off points of interest like pipe flanges on opposite sides of a factory, and you can get pretty much instantaneous measurements without processing any scan data. They're probably the most expensive option for a handheld, and they do require line of sight between the tracker and the handheld. So as you go around objects and around corners, you have to move the tracker along with you in various positions throughout the scanning process to maintain that line of sight. But they do offer good general mobility, and they hold excellent accuracy on large objects. They deal well with reflective surfaces. They're fast, generally very high performance. Another method is to use encoders in an arm to track the location of the laser as it collects the surface data, and that data can be mapped together using those coordinates provided by the encoders in the elbows of this arm. This is a really accurate way of tracking, and it works on all geometries. So it doesn't care if something is rich in geometry, like a marble sculpture, or flat and featureless, like the roof of a car, which is something we'll discuss more shortly. These scanners can scan chrome and other challenging surfaces, and apart from capturing scan data, they can use the touch probe to collect measurements really quickly without any data processing or cleanup. So these tend to dominate most QA, where parts are being inspected in high numbers. They need to be inspected with really high accuracy, and it needs to happen really fast. So these are good systems for inspecting parts, especially in a dedicated area, especially if the parts fall under a certain size range. Of course, not everyone is doing QA in a dedicated space. And while the arm is portable and it can be leapfrogged around objects bigger than the arm itself, it's easy to see how being tethered to an arm can lessen its versatility as a generalist scanner in certain ways. Another way is to use encoders in a turntable instead. So the turntable is in a fixed position in relation to the optics. And systems like these can be very accurate. This system is an Artex system called the Micro, and it's accurate to 10 microns. But you can see by the form factor that it has a hard size limitation. The automated nature of these turntable scanners can be both a pro and a con. If you're scanning small parts where only one side is needed, they're flat on the bottom, extremely convenient way to go. Whereas for complete scans of really complex geometries, you might require a lot of repositioning to get a complete scan, and you might find that a human wrist in a handheld scanner can collect it faster, but probably less accurately. Another way is for the scanner to stay in one spot, fire out laser pulses, just like a laser tape measure, and then the rotary encoders in the base of this thing can record the angle that each laser pulse is fired from. So you combine that known trajectory with the known speed of light for the distance to the object, and those two bits of information give you the coordinates of each point. That's how LiDAR scanners work. They're really good at scanning big objects like buildings, mines, airplanes, minimal hands-on work. But of course, they have their limitations too, especially when it comes to getting into tight spaces. So all of these scanners have certain conspicuous limitations, But in most cases, like the arms, the tracker, the LiDAR, the micro scanner, they are all extremely good at specific tasks and types of scanning, and they should be used accordingly. So if you're scanning buildings, you should definitely be using a LiDAR scanner. If you're inspecting hole locations on the same part 30 times a day, you should almost certainly be using an arm. If you're scanning tiny electrical connectors and stuff the size of Lego bricks with really high accuracy requirements, you should probably have a turntable scanner like the Micro. So the trend you're probably noticing here is that excelling at certain things, like elsewhere in life, tends to come at the cost of general versatility. Which brings me to the most versatile type of scanner and the most popular type, which is a structured light handheld scanner. And this is where understanding the tracking method gets important. One of the most attractive ways is to track with color and geometry recognition in real time, because it doesn't require that stickers be placed on an object. It's not tethered to an arm. It's not limited by line of sight with the tracking system. Doesn't need to stay in one spot. So it allows really good mobility. You can generally just pull them out, point and shoot. But of course, this has limitations too. A lot of people get the impression that these just aren't options for certain types of scanning. And that's true to a small extent. But if you understand how these work, you can work around those limitations most of the time. Or better said, they aren't real limitations, but more just considerations. So I'll show you some of the techniques that can be used to make these types of scanners work in a wider variety of scenarios, and why these types of scanners can be the best choice, in my opinion, for a generalist scanner. So these scanners are more economical than most of the types we just went through. So from a budget standpoint, it makes sense to test out an application with one of these before moving on to more expensive and potentially less versatile systems. Like I said, they're structured light. Some of them, have some other stuff in there like infrared lasers, but we consider this structured light so-called because it works by projecting a pattern onto an object and calculating its size and shape based on the distortion of that pattern. So just like this bike light, by flashing a grid, makes it really easy to see bumps and potholes. The scanner can do the same thing, and that's what it's doing here on the right with this distorted pattern. So there's some other stuff at play like triangulation, but it's this pattern distortion that's the primary mechanism. You should be aware that because they work by projecting a pattern made out of light, they can have some trouble in direct sunlight, a little more than lasers in general. And they can have more trouble with scanning shiny, polished surfaces than lasers. But that's an issue for all scanners, and it's usually solved with a little talc spray like we saw earlier. And there are even sprays that disappear on their own. They don't have any pigments or particles in them, and they just evaporate. And on the plus side, these structured light scanners can be higher resolution than lasers. They tend to be more affordable than lasers. They're often faster and have bigger capture areas. And some of them, like the Artex, can capture full color like you see here. This is a scan done with a full color handheld structured light scanner called an Artex Space Spider. It was the one you saw a few slides back that looked like a blue iron. And in the monochrome versions of the same shoe, you can see that the resolution these scanners can achieve is really extraordinary. They're also the only type of scanners of all the types we've just discussed that are any good for scanning people, which is in a lot of demand these days. And there's even a type of this type of scanner that's entirely wireless that you see here. This is the Artec Leo. So being able to scan without those limitations we discussed, it's attractive for obvious reasons, not using stickers, not having cords attached, being able to move freely. But that brings me to the most notable limitation of this type of scanner that relates to how it works. So like I said, these track geometry and or color. So you need at least one of those two elements. The map on the left is flat and it has no geometry to speak of, but because it has lots of color features, it's easy to scan. Whereas the plaster work on the right, it doesn't have any color features, but because it's rich in geometry, it's also easy to scan. But take these shapes. We discussed how scans are basically 3D panoramas, right? And the problem here is that there are no features that distinguish one section from another on shapes like this along their length. So there's nothing that you can use to relate one picture to another picture. If you make a little viewfinder with your hand and look at one 6-inch section of pristine stainless pipe and then another section, they look about the same. What's the full name of the 10-micron scanner I think you called the Micro? Someone has asked. It's called the Artec Micro. So it's made by a company based out of Luxembourg, and they have their US headquarters in the Bay Area, and they make a variety of scanners. I'll be demoing one of their scanners later on. So you can't really tell one section apart from another, right? And neither can the scanner. And that means that scanners that track purely by geometry and color are going to have trouble tracking or getting an accurate end-to-end measurement of objects like these, at least if the operator doesn't understand this consideration. And if they do, again, it's not a real limitation. There are a few ways of dealing with it. Artec scanners have the option of using photogrammetry, and I absolutely love that this company went to the trouble of supporting it, because it means that you have the option of using targets if and when you want. You know, if I'm scanning something totally featureless, like a flat piece of sheet metal or something like that, I can use this. And if I want really high accuracy, like say 8/1000ths of an inch over the length of a pickup truck, I can achieve that with one of these photogrammetry kits combined with an inexpensive handheld. So photogrammetry is not good at getting quality surface data, but it's really good at measuring between points over distance. So this can mitigate the accuracy loss you'd normally incur over distance with just a handheld scanner. So the way it works is you have this T-bar you see here. It needs to be put in the scene somewhere in some of the pictures. And you apply these targets, take a bunch of pics. You only need to apply these non-coded targets, the round ones, in areas where you want to collect the scan data. So those pictures get crunched in the software, and they generate a file that you bring into the 3D scanning software. And all of your scan data gets mapped onto it with much greater accuracy, like I said. This is more or less what it looks like. So they've applied those targets along the windowsill of the car because they're interested in that geometry. But if they were only interested in the distance between wheels, for instance, they would only need to put those targets on the wheels. So these can be a good solution for collecting data on separate isolated points without having to scan everything in between like you usually have to with a handheld. I don't use mine all that much, but I love having it, and I sleep better knowing I can provide this level of accuracy on big objects, regardless of whether they're geometry rich or featureless.
Yeah, and to jump into that, just to add on, I've found that it's actually really handy for scanning housing parts. For instance, I used it to scan part of my cabinet, and it made it so much easier to do my measurements around the cabinets, just because you only have to set up in certain areas and take a few photos to get a really good scan and distance mapping.
Yeah, there you go. But most of the time, there are actually less involved, more parsimonious ways of getting the accuracy I need without any specialized equipment. So, one option would be, we discussed spray, right? And how shiny surfaces like shiny black cars usually require it. You don't need to paint it completely opaque. A generous dusting is all you need to cut the glare. And you can see here that I've applied it in kind of a haphazard splotchy pattern. And that's by intent. It turns out that the color tracking algorithms in these scanners, they work really well with that. They can track these kinds of patterns very easily. So In this case, the spray can serve double duty as a tracking mechanism, as well as doling apart or making it opaque so that it's scannable. And it definitely beats cleaning off targets. Don't want to spray it? Maybe you can use some garage sale stickers from the dollar store. Or maybe you can mark it up with a dry erase marker. A few squiggles and X's here and there can do the trick. Don't want to mark it up? The background can often solve the problem. These two extruded shapes are the same along their length, but the floor isn't. It's covered with all kinds of gouges and divots and discolored areas, and that's all good stuff. The scanner loves it, and it can just fly over it. So maybe your floor is more pristine than mine. Add a few pieces of painter's tape. That'll do the trick. Or, for us geriatrics who still have paper maps laying around, we can throw down a road map, and these are full of unique non-repeating features like fine lines and intersections of all colors. So this is a great tracking background. Or you could use actual 3D objects. So a single trip to Goodwill and a $5 bill is going to get you all the tracking aids you'll ever need. This could be a go-to option if you're using a scanner that tracks geometry, but not color, like the Ava Light. And you can really use anything. I use lumps of clay all the time, and it could just be objects sitting around your desk, a few bottle caps and pencils, a computer mouse, and so on. If it's upright and you can't sit things on it, is it metal? Maybe you can use some fridge magnets. Maybe it's non-magnetic, or maybe you're not allowed to stick anything on it or touch it for whatever reason. The tracking aid doesn't need to be on it or touching it. It can just be something set up in front of it, like these alphabet blocks slid onto dowels that I keep around. Or a more improvised, simpler version of the same technique. This is just a piece of tape suspended in front of the object with additional pieces wadded up in several places along the length to add some geometry. So you probably get the idea. There are a lot of ways to skin this particular cat, and your imagination is really the only limit. So since a picture is worth 1,000 words, I'll go ahead and do some live scanning so everyone can get an idea of what this data processing looks like and what's involved from start to finish. So I have Artex Studio up, and I mentioned I would be using an Artex scanner. The one I'm going to be using is called the Space Spider. I'm going to show my webcam for a little bit so that you can actually see the scanner in real time. So this is the Artex Space Spider right here, very small, lightweight scanner. And I'm just going to start by pointing at the base, hitting the trigger, and scanning. And as you can see, this is a lot like spray painting. You tend to, angle your wrist and play with the distance a little bit and hit all the angles that you would if you were planning on spray painting this thing. And, if you want a complete part with the bottom in it, you're going to want to turn this into a few different positions. You can often get away with just two, but I find that things tend to be better constrained and more detailed if you do 3 positions on an object like this. This scanner doesn't have a hard size limit. I've chosen something pretty small, but you can go a lot bigger than this. And one more. All right, so we're done with the scanning part. And now we just need to process this scan data. So I'm going to go to my tools here. I had an option called automatic base removal turned on. That's what the blue grid you saw was. It had defined my base plane. And so now, as you can see, it's removed my bases automatically for me. I don't have to have this on, but it's convenient if you don't want the base in your scan. I need to align these, so I'm just going to hit auto align. Auto align isn't always going to work in every single situation. Here it's worked great, but if we just want to make believe that it didn't work in this scenario, this is how we'd confront it. We'd say the corner of the 5 is about here, this is about here, and this corner is somewhere around here. Align based on those points. I just have to get it in the ballpark and the software does the rest. So now we just want to run some cleanup tools on this, and I'll just switch to auto. This way I can just have things I want on, turned on or off. There's also an autopilot mode that you can use to just bluff your way through this program. It asks you questions like, is it a hard to scan surface? And if you have no context, it gives you examples. Is it medium or large? Here's what we mean by medium and large, and so forth. But here I'll just use these automated functions. And I'll just turn on the things I want on, like I said. Looks good to me. I'll hit go. So right now it's doing a global registration. It's taking all the various pictures of the panorama and it's fine aligning them with each other. That already finished. Now it's moved on to outlier removal, where it's looking for noise. It's removing things like dust motes in the air and reflections and what have you. And that's done, and now it's doing the final step, which is called a fusion in the software, and it's basically connecting the dots. We have a point cloud here, and now we're connecting those dots to create a polygonal mesh. So this should finish in just a second here. And then if we want, we can apply color on this thing. Now, you might have noticed the turntable I was using. Yeah, it looks pretty good. Very nice detail. We can see all the router marks in it, the wood grain. And if I want to do some other stuff, like this is 16 megabytes, let's say I want to email several of these, or maybe I want to display some kind of product on a website and I need the mesh to be really small and lightweight in size, I can simplify the mesh if I want. So I'll cut this down to 250,000 triangles. And that'll make it a lot smaller. As you can see, it's only 7 megabytes now. And now if we want this to be a color file, maybe we want to display it on the web or something, we can apply some color. If you have a nice graphics card, you'll probably beat me at this. My turntable here that you saw me using, it's just a cheap $15 plastic Lazy Susan from Amazon. You can buy fancy automated turntables that work with foot pedals and so forth. But this is actually my personal preference regardless of cost. So here we have the color on it, and we can mess around with these values, maybe brighten it up if we want. And when we're happy with it, there we go, we apply, and we have our scan, and we're ready to export this into a CAD, start creating a CAD model from it, or start putting it in a video game or whatever we want to do. And we can export this directly into SolidWorks, as you can see here, or we can export it as one of a variety of mesh formats. So I hope that gave you a better idea of how these scanners work, what's involved in scanning and processing, and how these various tracking methods might impact your application, how you can confront them, hopefully better than you did 25 minutes ago. So with that, I'm going to turn it over to Matt Fisher, and we're going to look at a technology from the opposite end of the spectrum that's very popular in QA. So all you, Matt.
Wonderful. Just going to show my screen now. And just to verify, we are seeing the PowerPoint slide.
I'm just going to answer one quick question before we're off to the races. Does it work well in bright sunlight? So because it works by projecting a pattern of light, if the sunlight is stronger than the light source of the scanner, it's going to wash out that pattern and it won't be able to see it, just like your human eyes won't be able to see it. So no, they don't tend to work well in really bright sunlight. No scanners work really well in bright sunlight, but the best case scenarios are single line lasers, because the compressed energy of a laser just does better at competing with the sun. So typically you want to use these scanners in in the kind of environment that would be comfortable for human eyes, like a kitchen or an office lighting. If you find yourself squinting, the scanner's probably having some trouble too. And the other question was, will this webinar be recorded and provided with a link? Yes, it is being recorded, and we're going to send a link out to everyone who attended and also everyone who wasn't able to attend. You'll also find it posted on our website. All you, Matt.
Wonderful. So what I want to talk about in my section is, we talked about the structured light, or Ian talked about structured light. I want to talk more about the laser scanning and CMM, specifically with the Hexagon brand, just because they are kind of one of the leading brands when it comes to probe and laser scanning. So to start off, we talked briefly about laser scanners, but what really kind of goes on in the background? So how these Hexagon arms work is they are, or in most laser scanners work, is they are encoders within the arm and the scanner. So it knows at what angle it's shooting out its laser at. And the laser is going at the speed of light, which is a known value. We have the known values of our angles because of these encoders. And based off of this, we can scan objects because that laser is bouncing off of the object back in the camera, and it knows its relative position. So what are some of the benefits that we get with laser scanning? Well, we can get really high accuracy due to these encoders and defined values. So we kind of get rid of that unknown assumptions, for instance, like with panoramas and global registrations. While they do get accuracy a lot of the times, this we don't really have to worry about our panoramas. It just, whatever it's pointing at, that's what it's scanning. We can also scan objects in the air or apart and not have to worry about in-between positions. Again, because we are basing all of our future data gathering off of a 0 encoded point, it doesn't matter where we're pointing the scanner at, whatever it interacts with, that is what it's going to be able to scan. So we can scan, pipes up in the air, or if we need to do that kind of situation where we're scanning one side of an object and then scanning the other side, we don't have to do anything in between. We can just scan the two and then, go from there. It's also very repeatable and with quality once the calibrations are complete. So most laser scanners and encoders, encoding scanners, you have to do a little bit of setup and a little bit of calibration based off of the scanning and fine tuning some of your settings. For instance, incident angle is a really big one, whereas incident angle is kind of the angle in which the laser is coming out at. You can adjust that. But once you have it set up, it's very repeatable. Most of the time, your scanner is not going to be moving from your quality control environment, so you don't have to worry about it coming out of calibration. You can just change the object that you're going to be scanning and put it in a designated area, and then just begin scanning right away. And then finally, it has no targets, which is very handy down the line. I mean, you can add the targets for the extra little bit if you want, just to maybe help out with some form of alignment, but it really is not required, and it really just goes a long way, not having to use these targets, not having to do this setup, really quick to just swap out your parts that you're going to be scanning. So next is going to be on CMM and coordinated measurement machine, and it's a very commonly used tool when it comes to inspection. And I felt like it was pretty good to add this into the scanning section, into this, even though it technically is not scanning, it's still used in conjunction with scanning pretty heavily, similar to photogrammetry tools. And as I mentioned, Hexagon arms and their bridge CMMs do have the probe tips, but can also switch between scanning if needed. And how these probes work is, again, based off of these encoders and the central points embedded within the device, you would be able to place your probe onto a part and take a snapshot of essentially where that probe is in space. So you can get extremely high accuracy, one of the highest forms of accuracy doing this, because it's down to the probe tip, with encoders in the probe, encoders in the probe's diameter, encoders in the arm itself, so you can know exactly where you are in space based off of where that probe is sitting. And again, technically it's not a scanner, but it is often used in conjunction. So for example, a lot of times people will be scanning, the top part of a sheet metal part with some hole locations in it. And while you can define those hole locations with the scanner, if you want that extra added accuracy for the exact diameter of those holes, that's where probes come in handy. You can nest your probe in the hole, take a few points, and then you know where that hole is and what its diameter is in space. So again, they kind of go hand in hand. And what I really like about the Hexagon arms is the fact that because they're embedded in the same thing, all you have to do is just a quick little flip of a switch, and you can switch between scanning and probing. So, where do these scanners excel? Well, they they excel very well within objects. So if you're scanning like PCB boards or any kind of sheet metal part inspection, this is really handy because we're not having to base off, when you are working with panoramic kind of situations, thin objects can have trouble because you kind of it doesn't have a lot of data to reference around. But with laser scanning, and it's based off of just where it is in space, you don't need to worry about making sure your panorama matches up correct to get that thin object. As long as they do not move at all, you can scan one side of an object and scan the other, and then you know what their distances are because, again, it's just in space. It's also great for scanning sections of larger objects. As I mentioned, you don't need to scan anything in between. So if you have like a long pipe flange and you need to scan, one part of a pipe and then, the exit part of the pipe or parts of car doors, you can just scan one side and then either move the scanner using Leapfrog, or just if it's close enough that you don't have to move the scanner, you can just scan the other side of the door, and there you go. You have your two sections of your part. Really great for hole positions and threads. And the reason why is because, again, that being able to kind of use those probes to get your thread, your hole positions. But with the laser, you do get a much more crisper line. Or a crisper mesh and data gathering. So you're able to get these kind of fine edges where hole positions really begin to shine. Objects with no feature is also great use for laser scanning and probes. And the reason why is because you're not needing to use any kind of feature recognition to generate your mesh and do your alignments. You can just scan across a flat surface and it'll appear as a flat surface, which is why also these scanners are really useful for flatness testing and inspection. And then also with clear and shiny object, laser scanners tend to be better than other kind of scanners. And the reason why is because of that kind of compressed laser. Even though an object might appear pretty dark and might not look like it's clear, a lot of times these laser scanners can really get into the finer detail and bounce off better. So for instance, the RS6 laser with the hexagon arm is one of the few scanners, or I believe actually one of the only scanners that can actually scan glass, which is unheard of due to that different type of compressed laser and the blue light laser scanning. But of course, not everything is perfect. Every scanner has its own benefits and downsides, like we talked about earlier. So where do these scanners have trouble in? Well, because it is a laser scanner, it cannot capture any color. Like Ian showed with the hexagon, or with the Artec Space Spider, we were able to scan that block and get the color and even that shoe's color. Unfortunately, with laser scanners, we don't really get that ability to capture color. We'd have to use a mixture of photogrammetry, so taking photos separately and applying that to our mesh is what we'd have to do. We also can't scan objects that can't sit still, such as people. Because you have that super high accuracy and encoded based positional data gathering, people tend to move. Even if you say that you can sit still, you're going to do little twitches. Even your blood vessels going through your hands are going to make your skin move a little bit, which the scanner will pick up on all these movements and thus distort the data a little bit. So if you can't sit your object still, you can't put on an inspection plate, these scanners might have a little bit of trouble. And also objects in small spaces it has troubles with. Because you are tethered to the arm, if you have to get inside of a car, you have to make sure that you have that kind of line of sight of the base of the arm to where you are within the car. So if you're trying to get into smaller spaces, you might have a little bit of trouble. Really where handheld scanners excel in is that you can get into the smaller spaces. But that's not to say that you can't use these scanners in small spaces. This is a pretty small scanner and it is a pretty long arm, so you can definitely get into tight spots. But if you're trying to get, if you're really moving in and out of tight spaces or really moving around really big objects that you have to leapfrog a lot, you can tend to find that this can get a little bit cumbersome and you have to kind of think not about where you're scanning and about how can I approach the scan. So with that, I wanted to go over just a brief demo. We talked about we showed off the structured light scanner, and I just wanted to go a little bit of an example on how laser scanners work. So I'm just going to bring over into PCDMIS, which is the software that Hexagon uses, and I'm also going to turn on my webcam just so. Actually, it looks like my webcam might not be able to show, but what I will do is kind of just scan two objects that are sitting apart from each other.
And while we're setting this up, I actually have a question here. Do these arms come in multiple sizes? And
yes.
The answer is yes, they do. You can get these arms in up to a 14-foot reach. And additionally, I alluded to earlier in my presentation that you can leapfrog around objects with them, so you can use them to scan objects that are bigger than the arm itself. And there's even a system called Gridlock available, where if you scan a lot of large objects in a dedicated space, like the same garage, maybe big truck chassis or something, a Hexagon technician can come out with a laser tracker and install these post systems where, you know, they're flush with the floor. You can drive over them with cars, they don't get in the way, but you can just swap around your arm from station to station without doing any leapfrog procedure. So yes, lots of sizes and a size capability beyond the size of the arm itself. Back to you.
Perfect. So what I'm going to scan, I have a little figurine standing up with its arms out in space, and then I also have a little block that I'm going to scan, just so you can kind of see how the laser works. So we have this kind of single line, and what it does is wherever it passes, you have a little calibration, but I'm holding down the trigger, and as I kind of go up, it's gathering millions of points of data at once. So I can just hold down the trigger and kind of just go across, scan an object. I let go of the trigger and we get our data, point cloud data. I think we might have mentioned this previously, but most scanners always gather in kind of a point cloud format, and then you take these point clouds and turn it into a mesh using triangulation. So if we have this, I can now zoom in to this a bit closer, and you can even see the bands of lines of where it's gathering this data. So this is where the laser scanners kind of shine. Again, it's just saying wherever we're looking at, that's where we're going to gather our data. And because of that, if I let go of the scanner and put it down, I don't have to worry about making sure I have to do an alignment. I haven't moved my object, so all future scans are going to appear correctly. And even the arm that's out in space, I'm able to go through that, gather it, no problem at all. I don't have to worry about making sure that I'm gathering things in the background, like we had to put those blocks around to keep our tracking. This is able to gather in space. And then even I can go off to the side. So something I haven't even measured once yet, it's in a different part of my table, I can start scanning this as well, and it's starting to appear too. So this is really handy if you just need to gather certain spots regarding inspection. Another kind of downside is if you have to move this around, you do have to do your alignments. It's not going to automatically do alignments for you. So if I happen to move my block into a different position to rescan, I'm going to have to align between these two now to be able to complete the picture of the block. But still, able to gather data very quickly. I have millions of data points of data at once. And again, we can zoom into here and just see the bands like beforehand. But we have the situation like this oval right here, or this circle right here. I didn't really gather the data, but you know what? That's okay. The reason why is I can just switch over to the probe mode. So I'm just holding down my trigger. And now I can load in a probe. And from here, I can just start gathering data again with the probe. I can even go a little step further and do something called quick measure. So if I want to just quickly measure, let's say a hole position or a hole diameter, I can click on this and it'll ask me to just take a plane measurement. And now I can gather the position of my hole. Just 3 points. 30.12, I believe this hole diameter is 30.1, so very accurate to what it was. And if I click OK, it actually even kept that in my data space. So I can even see, this circle right here was where I first gathered the plane. And then I can see this circle 2 is actually the circle of that middle part of the block. So super quick to switch between. Yeah, we're having issues with the webcam. It's not letting me show it, unfortunately. I wish I'd be able to show the arm in action, but it's having trouble with the webcam.
That's all right. If anyone wants to see this first person, we're happy to give you a private demo. Just reach out to us.
Yeah. So with that, I can send it back over to Ian.
Well, here is my contact up here. If you have questions, no matter how elementary, if you want to learn more about scanning, want to see a demo, want us to scan something custom for you as a benchmark, we'd love to hear from you, whatever the case. So go ahead and shoot me an email, give me a call, look us up on the website, however you want to do it. And with that, we'll go ahead and end here. Thank you, everyone, so much for attending.